In this video, we look at the definition of FM and PM. FM means frequency modulation, which means that the frequency of the carrier is changed by the message, which means that the message signal is carried by the carrier frequency in the carrier signal. The phase modulation, which means that the phase of the carrier signal is changed by the signal. In other words, the message signal is carried by the phase in the carrier signal. FM and PM are both called angle modulation. And angle modulation is nonlinear. It's more complicated than the AM modulation because AM is linear. Now let's explain why AM is linear. Like suppose I have a message MT. It can be decomposed by two parts. So MT is a linear combination of M1T and M2T. Now, for example, if I use DSB-SC AM signals, if I modulate FM directly, so U of T equals to MT multiplied by C of T, right? And then now if I modulate MT, I will obtain the modulated signal using M1T. So the modulated signal for M1T equals to U of 1T, that equals M1T multiplied by C of T. Suppose we use the same carrier. U of 2T equals to M2T, C of T. So now if I sum them up, if I sum the modulated signal, which comes from the individually modulated signal for M1T and M2T, this happens to be equals to U of T. So therefore, this AM signal is linear. Linearity is always a very desirable property for any scheme because it just makes things easier. Now let's define the angle modulated signal. It has a general form of U of T equals to AC multiplied by cosine 2 pi of C plus phi of T. And this phi of T is defined differently for FM and PM modulations. So I write it. This is a general modulated signal for FM and PM. And FC, that's the carrier frequency in the carrier signal. Phi of T is defined as Kp multiplied by MT for PM signal. For FM, it's defined as 2 pi Kf integral from minus infinity to T m tau d tau. And MT is the message. In other words, for FM, we take the integral from long time ago up to the current time, and then multiply by 2 pi Kf. That's equals to phi of T. Both FM and PM, the angle is this portion is changed with the message, but in different ways. For PM signals, we can see phi is proportional to the message directly because it's multiplied by K of P. Kp is positive. Kp is the phase deviation constant. Because of this term defined by Kpmt, the maximum phase deviation is defined as delta phi max. Max means maximum phase deviation equals to Kp. We're going to take maximum value of absolute value of Mt. So this will give the maximum phase deviation. Next, let's look at the FM modulation. We have phi of T equals to this portion. Now let's look at the instantaneous frequency for FM. I use notation Fi. I means instantaneous. How we calculate the instantaneous frequency? We take 1 over 2 pi and the derivative of the angle is this portion. Not phi of t, but 2 pi of ct plus phi of t. Because this whole thing is the angle for the cosine signal. If we want to find the frequency for a cosine signal, we want to look at the angle here. So that's equals 2 pi of c of t. I plug in phi of t here. 2 pi kf. Now, and 2 pi cancel out each other. Right? And then that equals 2. If we take derivative of this, that's fc plus, if we take derivative, and this is an integral, and integral and derivative cancel out each other, that equals kf mt. So this is the instantaneous frequency. This is exactly what we got here. If we take the difference of the instantaneous frequency and the carrier frequency, difference is proportional to the message. The maximum frequency deviation for FM modulation is delta F max. Again, this notation delta F is one notation. Max means maximum. This is instantaneous frequency that equals FC, that's a constant, and this term is changing. The maximum frequency deviation is KF, then multiplied by max of absolute value of MT. What's the power in the modulated signal for both PM and FM? That was equals to AC squared divided by 2. So this is the P of U equals 2 for both PM and FM.